It's all right.
Is it on? Yes. Great, thank you.
Right, our next speaker is Jay Lockman. He's going to talk about the discovery of diffuse atomic interstellar clouds in 2002.
Thanks very much. I'm going to claim that we finally discovered diffuse interstellar atomic clouds, but it took us to 2002 to do it. But first, it's not been mentioned, but 50 years ago this month, a young hippie, beaded, bearded, tattooed, pierced, managed to convince Princeton University to give him a PhD, and that's Carl Heiles. And in fact, I have his thesis right here. He used all of the modern technology that was available at the time, fold-out, scotch-taped, contour maps, hand-drawn, and it's really an amazing work. And I'll have it around the rest of the meeting for those of you who want to marvel at it. Carl did observations of interstellar hydrogen and summarized them by saying that he saw a background component, a large clouds of hydrogen localized in space, which I find very difficult to find in his contour maps, and smaller clouds of hydrogen cloudlets localized in space and velocity. And the whole concept of an interstellar cloud has been a very fuzzy one, at least a diffuse atomic interstellar cloud. You look at the observations and things tend to be blobby or sheet-like or blended, heavily blended. And the situation changed in around 2002, when for the first time we were able to look at interstellar hydrogen with the Green Bank telescope. And what this shows is a cut through the galactic plane, latitude, velocity. And you can see right away that all of these little blips here are in fact hydrogen clouds that are distinct in velocity and distinct in space. And we see them because we're up out of the muck of the plane. We also see them because they have a somewhat higher velocity than the rest of the material. Here's what you expect from co-rotation. And so you can see that a cloud like this obviously must be fairly near the tangent point, which gives us a distance. And in fact, we can actually calculate reasonable errors on the distance, and from that fall out all the physical properties of these kind of clouds. And so they've picked up the name disk halo clouds. I don't know whether that's appropriate or not, but I'm just going to run down some of the literature on it. Still et al. Found that these clouds extend right down into the galactic plane. Confusion is always more of a problem, but we believe it's a pervasive population in the inner galaxy. Oops, I missed. From Arecibo data, Stanimirovic, Strasser, Ditas, and others, we're finding clouds in the outer galaxy. These it's more difficult to get the distance to, so I won't mention it. And Allison Ford established some statistics of the population by looking at a few hundred clouds. The cloud-cloud velocity dispersion is 16 kilometers a second, and depending on where you look, the scale height is a few hundred to almost a kiloparsec. Here's an example of some of them, and this is Green Bank telescope data here. This is data here from Parkes. And if you just take a velocity slice, here's the galactic plane, you see all these little things like this scattered around like that. And here are some of the ones that I'm going to be talking about in this talk. A few things to emphasize. This is a galactic population. These clouds follow galactic rotation. If you go a half a kiloparsec out of the plane and determine a rotation curve from these clouds, you'll get about the same thing you do down in the plane. Their numbers increase toward the galactic plane, and so these are not some high velocity cloud phenomena, not some interloper, it's galactic material. And finally, they seem to be in some general sense tied to the products of star formation. And so a group of us now, led by Yuri Pito-Prihora, with John Dickey and Michael Rupin, looked at a number of these with combination of Green Bank telescope and the VLA to get 1 arc-minute resolution. And what we were really doing was now using these clouds as a test population, because as was mentioned earlier by Adam, theories of interstellar medium make strong predictions about the structures of the clouds as a function of pressure, for example. So we picked a group of clouds that had this distance from the galactic center, a variety of distances from the galactic plane. We used 1 arc-minute resolution, and here was our sensitivity. And I'm going to just show part today of the 10 clouds that were part of one sample. We've got higher resolution data on others that has yet to be analyzed. For the geeks of you, no, I'm not even going to mention that. But let me just mention, you can look at the brightness temperature of the VLA spectra compared to the GBT spectra, where the beam areas differ by 2 orders of magnitude. So in principle, if you have unresolved structure that's a good component, a fair component of the total, you could see brightness increase by a factor of 100 between the VLA and the GBT. In fact, the median is only 4. So we really have resolved most of the structure with the VLA observations. And here's just a sample of the clouds, their position, distance from the galactic center, and distance from the galactic plane. Okay, here's the gallery. And this is ordered by increasing distance from the galactic center. And there's 9 of them. Since this cloud's not so interesting, I'll overlay the 10th one on top of it. Actually, it's very interesting, but for a different reason that I'll get to in a moment. And here's how some of these clouds look like in cuts through the galactic plane, latitude, velocity. There's one of them up there. And there's another one down there. We can get out the mass. And here at the mass, it's the mass of a Spitzer standard cloud, a few hundred solar masses. From this one, which is special, all the way up to almost 1,000 solar masses. The edges are sometimes not so distinct. And here's what a channel map of one of them looks like. And that is the total hydrogen column density. I'll get back to this cloud again in a bit. Here's another example of a channel map and the total hydrogen column density. And you can see a scale put on there. And one more. We have one cloud of this sample that really stands out, and that's the one at the lowest longitude. Not closest to the galactic plane, but the lowest longitude. This G16 is just a small, compact, cool cloud. And look at one here, which is only 1.5 degrees away on the sky. In fact, if they're both at the tangent point, then these clouds are only about 135 parsecs apart in the Milky Way. Although given the uncertainties, they're probably more like a kiloparsec apart. What's so interesting about these two is that this is a close-up of this G16 cloud, and here's its line width, 4.6 kilometers a second, simple, cool line. And here's why I think it's so interesting. This is a diagram of the hydrogen versus longitude and latitude, Parkes data, GBT data, and you can see this big void in here. Naomi McClure-Griffiths and I just published a paper equating this to the Fermi bubble, the region that is evacuated by the hot wind at the galactic nucleus. If we look a little more, if we look a little more closely, here's where G16 is, and here's where G17 is. And so it's quite likely that this cloud is actually within the nuclear wind. The high pressure has driven it into a pure cold phase. Whereas by the time you get here, you're back out in the normal interstellar matter. Okay, a little bit about the structure of the clouds and specifically their line width. This is that cloud G17. It is 300 parsecs from the Milky Way. And here's a couple lines and their line width. You can see this is a fairly broad cloud, 13 to about 18 kilometers a second for the different line widths. This has a tail that extends back toward the galactic plane. This is G6. What is this? G16 again, Okay, G19.5. Now we are 500 parsecs below the galactic plane, a pretty big cloud. And here we see a fairly uniform line width at different places in the cloud, even towards the brighter parts and towards some of the fainter parts. This is about 600 parsecs above the galactic plane, and here we see some very interesting structures in the line width. Towards the brightest part of the cloud, we actually see 2 different components, a broad component and a narrow. Up here we have a broad component and then a very narrow component. So we really are seeing regions that have very different physical properties at different places in these clouds. And I think this is one of my final examples. Again, broad lines, lines with definite wings. It can't be fit by a simple Gaussian, and narrow lines all scattered around in different parts of the cloud. This is an interesting one because this is the GBT map. It is this lump in what is a chain of clouds, and we have data on all three clouds. And finally, I think this is my final one. This one is a kiloparsec below the plane, fairly modest cloud, and we have still cold regions of very cold gas. Oh, this, by the way, is a blow-up of the spectrum toward the peak, again showing two velocity components. Okay, so here's what we've got. If you look at just the full width half maximum toward the brightest part of the clouds, we have some that seem to be fit with one component, but some that definitely require two components to fit the line. We can identify cloud cores. These are regions of enhanced density, and here's a list of them. Here's the mass, about 50 solar masses. That first cloud that's in the Fermi bubble, it's nothing but core, but the rest of them have it about the same, 50 solar masses. And we have here some information on the implied temperatures and limits on temperatures. Gosh, I think I am missing a table. Oh, just the peak column density over here. All right, so let me end by saying that, are these a separate category of clouds, or are these pervasive in the interstellar medium? And we can only see them when you get to locations in velocity and latitude where confusion is low. I don't know, but I think these are fairly pervasive, and are they simply interstellar clouds that we're able to see for the first time? Let me just mention that this work has been possible because of the Green Bank telescope, and I'll just, in case you haven't heard, the Green Bank Observatory on October 1st will be split off from NRAO, made into its own new institution, and so we're busy getting library subscriptions, new internet addresses, hiring a web designer, all these efficiencies that the NSF demands. And the NSF's plan is to reduce funding for basic research by about a factor of 3/4. In other words, down to 1/4 of its current value over the next few years. So we may be seeing the end to a lot of this kind of research that is being presented at this meeting. I'd be happy to answer questions about that offline, but for now, let me just leave you with this image of this amazing cloud. Thanks.
Is enough known about the temperature distribution around the clouds to say anything about whether they're in pressure equilibrium with the surrounding ISM or not?
We really don't know much about the surrounding ISM. It would be my answer to that. So the answer is no, we don't know.
Maybe from the Fermi data we could get some, at least in the clouds inside the Fermi bubbles.
Oh, the cloud inside the Fermi bubble, yes.
We had temperature data outside of it, so then you could estimate if they're in pressure equilibrium or not.
Yeah, if you just look at NT, then that's lower than what you would expect inside the Fermi bubble.
So in the clouds where you have only one component, is that real, or to what extent is it a single noise effect that you can't see the broader component? Can you tell whether it is single component in some clouds really, or is it single noise?
Yeah, good question. All of these clouds would benefit from doubling or tripling the integration time. And so, and also to imply the way I did in that table that there was a single value for a single cloud is incorrect. We see a lot of structures throughout that. There certainly could be faint, broad lines that we are missing in the high resolution data. We will see them in the GBT data.
Let's do Blair in the back, and I think we might have to wrap up with this one.
Very nice talk, Jay. But I'd like to make a historical comment.
The mic.
And
Mike's not on, I don't think.
it's on? Is it on? Okay, I'm pointing it the wrong way. Very nice talk. And actually seeing those clouds in H1 emission as isolated entities is wonderful. But I'd like to make a historical comment. Clouds have been seen for many, many years. Depends on what you mean by seen. But they've been seen in absorption, optical absorption, ultraviolet absorption. So if you go back to the various texts of Spitzer, they're extensively discussed. And you can measure detailed properties in individual clouds through that absorption spectroscopy. And what's the basis for that? Well, if you look at a line of sight to a star at, 500 parsecs in a disk, you'll see something like 4, 5, 6 sodium-1 absorption components, carbon-1 absorption components. It's a complicated structure of absorption separated kinematically from one absorbing species to the next. And within those entities, you can determine physical conditions and such things as temperature, pressure, and so on. So it may not be under the broad guideline or broad definition of seeing, but you can see what's missing, and from that infer the existence of organized, isolated entities along a line of sight to stars in the disk.
Yeah, that's always been the tension between the emission experiments and the absorption experiments. And I have learned from the work of Lazarian and many others, though, that one can make kinematic structure without really, due to turbulence, without really having this kind of spatial organization, which is what we think of when we have clouds. But both lines of inquiry, equally important.
Another approach is to, in a general direction, look at stars at different distances.
Oh yeah.
Nearby, further out, and you see the increasing number of these kinematic structures as the distance increases.
Sure, yeah.
Okay, we need to move on. I know there were a lot of other questions for the last two talks. Please save them up and address the speakers during our lunch coming up.